We've been given the task of comparing two different warranties. Specifically, we want to know which warranty, if offered with the purchase of the vacuum, would drive more revenue per visitor. We've been asked to set up a test where we generate two samples, one with each warranty. We let our test run for 2 weeks. At the end, we have two samples of 750 visitors. One that was shown the 5-year full warranty, and another that showed the 7-year limited warranty. After the 2 weeks is over, we collect data, and here are the results. With all this done, we just have to compare the means of our two samples, and we can see that the 7-year limited warranty has a mean revenue per visitor that's about $7 higher. We have a winner. Right? Well, perhaps the difference we observe is just the result of random chance. Perhaps it has nothing to do with what our visitors think about the warranties. Or maybe it's not random, and the 7-year warranty really is better. The hypothesis test we'll explore in this chapter attempts to provide an answer to questions like, how likely is an observation just random chance? In a hypothesis test, we start with an assumption about our population parameters. Remember, we know our sample means, but not our population means. But for our test, let's assume that our two populations aren't different from our 5-year sample, and the higher 7-year limited warranty value was just random chance. Next, we can apply math to see how likely it is to get a sample of $62.51 if our population mean is $56.30. The hope would be to show that sample to be improbable. In logic, this is known as reductio ad absurdum, or reduction to absurdity. If we can show, through statistics, that randomly pulling a sample this extreme is highly unlikely, we can then reject that assumption. To start our hypothesis test, we select one sample and model the expected distribution around it. We can guess that distribution by measuring the standard deviation of our samples. The test then sees where on the bell curve our second sample falls. We can then calculate the area of our distribution that is as extreme or more extreme than our sample. If our second sample fell fairly close, say 0.5 sigma from the center, then about 62% of the area of our bell curve is that distance or farther. So there's a 62% chance of getting a sample that extreme, based on our assumptions. 62% of the time is quite frequent, so this result is not really unusual. However, if the difference was larger, or the spread of our data was smaller, our result becomes more extreme. Now the second sample falls 3 sigma from our center. We'd only expect to see results this distant 0.3% of the time. That seems rather unusual. Therefore, it would be reasonable to reject the assumption that the differences are purely due to randomness. Put a different way, 99.7% of the time, we'd be correct in rejecting the idea that the population means are the same.